Can you guys see my screen?
Yeah.
Awesome.
Yep.
All right, we'll go ahead and get started. So, hi everyone, welcome to our second general body meeting. We're going to start with an icebreaker, your name, major, what year you are, and then the question today is what song always makes you dance or sing along? I will go first, and then if either Erin or Megan could read through the names for everyone, that would be great. So I'm Michaela, I'm a civil engineer, I'm a second year, and the song that always makes me dance or sing along is September by Earth, Wind, and Fire. So.
Is that the song that you said that you have stuck in your head right now?
Yes, that's I don't know, it's just one of my favorite songs. It's just very happy.
That's good. I'll go next, I guess. I'm Megan. I'm a third-year mechanical engineering student. I don't know. I love all the bops. Okay, play anything from the 2012 to now, and it's a bop. 2012 to 2018. Those were the real bops, you know. So, but I don't know. I now have that song. Was it singing in the shower? I don't know how it goes, but it's terrible. I can't sing. I have that song stuck in my head. But Michaela, do you want to go down the list, or do you want me to?
I can't see it because I'm sharing my screen. So
okay, I'll do it. Andrew.
Hey guys, my name is Andrew Needs. I am a civil engineer and I am a 7th year, I guess, by counting. And what song makes me sing is pretty much anything by Rise Against.
Anna.
So, hi, I'm Anna. I'm a second year civil engineer, and a song that always makes me sing is Party in the USA.
That's bop. I had this stuck in my head earlier today. Sorry. I love it. It's a good song. Ashley?
Hi, my name is Ashley Knight, and I'm in chemical engineering in my 5th year. And a song that always makes me dance and sing is Man, I Feel Like a Woman by Shania Twain.
Shania Twain's bop. We love that. Brooklyn?
Hi, I'm Brooklyn. I'm a first-year biochemistry major, and a song that always makes me dance or sing is any early One Direction.
Those are bops. I love the word bops. I'm so sorry. You guys are going to hear me say it 6 more times. I always talk about songs as bops, okay? Chris.
Hey guys, my name's Chris Tavarich. I'm a 4th year mechanical engineering major. And this summer I started listening to the Hamilton soundtrack a lot.
Hamilton?
Yeah. Yeah, you should give it a shot. But yeah, that's what I've been listening to.
What is your favorite Hamilton song?
Probably My Shot. But
I was gonna say, don't throw away your shot to see it on Disney Plus because
yes.
It's good.
Michaela. Erin.
I'm Erin. I'm a second year electrical engineering student, and I'd have to say that One More Time by Britney Spears.
There you go. Isabel?
Hi, I'm Isabel. I'm a mechanical engineer first year. And then a song that makes me bop is Put Your Records On.
These are bops. I'm gonna say it again and I'm not gonna apologize. Jacob?
Hey, I'm Jacob. I'm a fourth year mechanical engineering major. And for a song, I'm gonna say Funky Town. That song is infectious.
That'll get you. I'm gonna have like all of these stuck in my head later. I don't know about you guys. Kayla?
Hi, I'm Kayla. I'm a fifth year in chemical engineering. Probably anything Paramore.
Keith?
Hi, I'm Keith. I'm in my final semester of electrical engineering. I don't really dance, but sing along. 9 Inch Nails, Perfect Drug.
Lordy.
Hi guys, I'm Lordy. I'm a fourth year accounting student. And a song that I really like to sing along to is My Sweet Lord by George Harrison.
Okay, what? Molly? Who's Molly?
Hi, I'm Molly. I'm a fifth year computer engineer. And the song that makes me sing and dance is Beautiful Girls by Sean Kingston.
And then Oleinka.
Hello, I am Oleinka. Oleinka Famadu. My major is I am a biomedical engineering, and then my year is third year, BME. And the song that makes me dance or sing along is I Wish by Stevie Wonder.
Nice. And I think that's everyone, Michaela. Right. Did we miss anybody?
Brian, did you want to participate?
Oh yes, I was gonna ask at the end. I'm sorry.
Yeah, sure. My name is Brian Gresser. I'm a mechanical engineer. I graduated in 1989. And I guess a song that makes me sing would be probably maybe Dancing Queen by ABBA.
That's a good one. I feel like you learn a lot about people from like the music they listen to or their favorite songs. So that's always fun. All right, so just a few quick reminders. If you are not on Slack yet, please get on Slack. You can join via our website, and also there should be a link to do that in all of our emails. It's just a faster way for us to communicate instead of constantly sending emails. And we also have some fun things on there. Like we have a memes channel. We have one about sustainability in the media. So if you watch like a cool documentary or something, you can talk about that. So it's just a good time.
If you're confused or would like assistance with getting on Slack, just like email one of us or email the ESW Akron, and then we can help you out from there. Yeah. I know it can be a little daunting, but it's really nice once it's all set up. And it takes
and we can even, if you just send us a quick email to ESW Akron, we can even add you manually. So then all you have to do is like, it'll send you an email. So it's super easy. If you would like to purchase a t-shirt, there's our link. You can also find that link on our website. We are hoping to kind of clear out the inventory of these t-shirts and then start looking into a new design. So if you're interested in designing a new t-shirt, feel free to contact one of the officers. Next, please connect with us on LinkedIn. Me and a few of the other officers were talking, and we noticed it's kind of difficult to find like sustainable co-ops and just jobs in sustainability in general. So we made a LinkedIn page for Engineers for a Sustainable World and are kind of making a network of sustainable contacts and just companies that at least have a sustainability program. So if you connect with us on LinkedIn, you'll gain access to that whole network. And then if you know of anybody who, whether it's a contact who works in sustainability or, a company that, does sustainable practices, please let us know. And then we will add them to our LinkedIn network as well to try to make it easier for future ESW members or just students in general. It'll be easier for them to find those sustainable jobs. Some project updates. Megan, if you want to go ahead.
Sure. So I'm the education team leader. We do K-12 educational presentations. So we have a couple lined up for Earth Day. So I'm super excited about that. And then we also have some independent projects that you can work on. Like you choose that, you work on everything at your own pace. Our weekly meetings are on Wednesdays at 6:30. Even on general body meeting days, we'll meet, but all we're doing is like a quick 20-minute check-in and like do a task anytime you want during the week and like just real small chunks. So if you're interested in doing community outreach in K-12 schools or anything, any environmental topic that you want to do more research on, you can make a cool presentation and you can check out examples on our website of completed ones. They're super awesome and people took a long time to do them. So I recommend checking them out. So yeah, that's my time.
All right. I don't think Nora's here. So if either Kayla or Keith want to present on ZPP, or I can. Okay, I'll take that as I will do. Oh, go ahead.
So currently we're working on finishing up building the extruder, and we're going to start programming once we have it all put together. We're also working on finding a more permanent space soon, so hopefully we'll be able to operate once we have this equipment all finished. And we meet on Thursdays from 5 to 6. So this week it's going to be on Teams, and we're going to be meeting with some past members to discuss the design so we can finish building. But occasionally we do meet on campus to build the equipment.
Yeah, and ZPP has made a lot of progress, like just in the past few weeks. It's really kind of cool. Bike power.
So currently we are meeting at 7 on Microsoft Teams, and so starting the week of the 15th, we haven't finalized a time or day yet of that week, but we're hoping to meet in person so we can actually attach a generator that we ordered onto a bicycle, just because we have a lot of the I guess parts ordered and stuff. We've done a lot online, but now we're hoping to meet in person. So if you're interested, please feel free to reach out, and hopefully after we get this generator, we can start adding the technology and the batteries. So yeah.
And something else to look forward to, we're hoping either, if not at the end of this semester, at the beginning of next fall semester, we're hoping to do like a ESW bike ride to test out our bike-powered generator. So just keep your eyes open for that. Wind turbine.
Hey, I'm the project leader of Wind Turbine. So we meet Mondays at 5. We're currently in the very early stages of this project. So we're still trying to get funding and kind of in the proposal phase. We might have funding. I'm still waiting to hear back on one. So we're currently trying to move more into some individual research into like certain components on the wind turbine. So like the blades, the generator, the battery, so we can kind of get more information on those individual parts, and then we'll bring it together in the end. And we're trying to get a final kind of general layout of what it's going to look like. So if you're interested in helping us out with that, let me know.
All right. Other opportunities, and before I go on, just if you haven't yet, in the chat there is a link to fill out an attendance sheet. If you would fill that out, that would be great. So we are doing something new. We are doing a Friday social hour. We've done it for 2 weeks now, and it's been a lot of fun. They're hosted on Teams, so this same link would get you into our Friday social hour. Everyone's welcome. Please bring your friends. Over the past 2 weeks, we have just talked about our weeks, complained about classes, talked about what we were making for dinner. It's just been fun. But this week on Friday, we're going to hopefully do a few games, and it'll just be a good time. So if you can come, please do. Another opportunity, we have our virtual conference coming up. So it is the week of Earth Week. You can find out more information about it here at some of these links. The student registration fee is $40. But if that's something, if you're really passionate about going, but that's not an expense you can do, please let us know, and we can possibly get you a sponsorship to go or a scholarship. And lastly, we also have our mentorship program. So you can find a link at the bottom of all of our emails. And so if you're having a hard time with anything, I mean, whether it's classes, just in general college life, if you're stressed about co-ops, future plans, you can fill out that form, and it'll be confidential. We'll reach out to you, and you can just talk to one of the upperclassmen in ESW, and yeah. And then here are our next general body meetings. These can all be found on our website and in our emails that we send out. And without further ado,
I was going to say real quick, on the general body meeting, we're going to do trivia night next general body meeting. So we would like to know, I think we're going to go with a Kahoot. So if you have any suggestions for topics that you'd like to see in that Kahoot, throw them in the chat. Or if you think of them, then you can email them to us or throw them in Slack.
Or if you would like to create a Kahoot and do it, we can do that too. Thank you, Megan. I forgot about that. All right, so now, without any further ado, we're going to be hearing from Mr. Brian Gresser. He is a professional engineer and manager at the City of Akron's water reclamation facility. Mr. Grusser, do you have PowerPoint slides or?
I do, yes.
All right. I will stop sharing then.
And then you might have to help me. I'm not most familiar with Teams. I'm a kind of a Zoom guy.
So up at the top by where you can turn on and off your microphone, there should be a box with an arrow going up into it.
Open share tray.
Yep, and then you can just click. I always use my current screen and then just navigate to my presentation.
Can you see that?
No.
No. Bear with me. Application. You see that?
Yes.
Okay, we good?
Yeah.
Okay. Again, my name is Brian Gresser. I am a graduate of the University of Akron. I'm a mechanical engineer. Like I mentioned, I graduated back in 1989 and have stayed local for the most part and have spent my entire career at this facility you see on the screen here. And this is the wastewater plant for the city of Akron. And it's located down in the Merriman Valley. I'm sure many of you have probably driven past there, maybe have smelled us in the past, but that's where I'm at. And basically, I'm going to talk today about a number of things that we're doing kind of on the sustainability side. And please, if anybody has any questions, interrupt me at any time, and we'll kind of make this as interactive as we can. So I'll talk a little bit about the combined sewer system in Akron. We have a large, pretty expensive, over $1 billion program going on right now of building sewers and solutions to solve our combined sewer issue in the city. We're also doing improvements at the water reclamation facility, which is the wastewater plant. And then also our renewable energy facility, which is located on the other side of the Cuyahoga River, which is where we process the biosolids. And then we also do some cogeneration, and I want to talk a little bit about landfill gas that we've done in the past. So just a little bit about, I'm sorry, go.
We're still seeing your first page. I don't know if you like went into presenter mode. I don't think we're seeing that. There we go. Thank you.
If I'm in presenter mode, will it not show then? Is that the problem?
Yeah, I don't think so. We've had difficulties with that before. So.
Okay, well, I guess we'll try to stay here. Maybe I'll move this over. Try to make this as big as possible. All right, so I apologize if it looks like it's kind of chopped off a little bit, maybe. This is Akron's collection system area. So we not only treat the city of Akron, but most of the local communities like Cuyahoga Falls, Talmadge, Springfield, Lake Moore, Mogador, Fairlawn, and then also some unincorporated areas of the county. If you're not real familiar with the lay of the land, I highlighted the university there right in the center. So it's basically right in the center of our collection area. There you see some statistics. The population serves about 330,000. We've got about 85,000 active sewer accounts, 36 pump stations. We're actually lucky in the Akron area. The topography allows us to gravity flow most of the sewage to the treatment plant down in the valley. So while 36 may sound like a lot, it's definitely not compared to some communities like Phoenix out in Arizona. They have like 400 pump stations in their collection system just because it's so flat. We've got 26 CSO structures I'm going to talk about in a little bit, 861 miles of sewers, and almost 20,000 manholes in our system. So Akron largely grew back in the early part of the 20th century when the rubber industry started booming. A lot of homes and infrastructure was built in the teens, 20s, and into the 30s to support that rubber industry. And sewers back then were built of a combined nature. And basically what that means is rainfall and sanitary flow flows to this in the same pipe to the treatment plant. But during periods of high rain or a lot of rainfall, there's outlet structures that, if you can see my cursor here, that allow those pipes to overflow into a river or stream. In our particular case, it could be the Cuyahoga River, the Little Cuyahoga River, or the Ohio Canal. This was a pretty common place. There's about 800 communities in the United States that have combined sewers, but it's a deal breaker now. These types of sewers were built up until the 30s and 40s, and then we've been spending now most of our time trying to resolve the effects of what these combined sewers cause. This is a picture of a regulator structure. So the larger picture, the wastewater is actually flowing from the left, and it drops through that, what we call a bar rack, and down into a sanitary sewer then that goes to the treatment plant. If this pipe were to take storm water because of a rain event, this flow would inundate this rack and flow past the rack and out something similar to this, which would be an outlet to a stream. So at that point, you're actually putting raw sewage out into a stream, albeit it's very dilute. It's probably only about 1% sewage and 99% stormwater. But nonetheless, there's a bacteria situation where you're putting this bacteria into a stream. Akron CSOs mainly are confined to the central part of town where the university is located. They're see here, for some reason it's not showing up. Wait a minute. I apologize, since this isn't going full screen, you're not seeing it all. So 18% of our system has combined sewers, so that's about 157 miles of combined sewers. And we're involved in this 17-year program to resolve these combined sewers to the tune of $1.2 billion. So we've worked with the regulators, US EPA, the Department of Justice, Ohio EPA, to come up with a plan to resolve these combined sewers. And it basically involves a number of things. One is storage basins. We've been building a number of storage basins across town, anywhere from 10 million gallons down to 1.5 million gallons in volume. And basically what those storage basins do is they act as a retainer. They capture the water that's overflowing out of the CSO structure, and we hold flow in those basins for a period of time until the treatment plant is capable of accepting it. And then we release that flow to the treatment plant for treatment. We've got 2 tunnels that'll be in our program. One is the Ohio Canal Interceptor Tunnel. You may have heard about this project here over the last number of years. It went online in 2019. It was a little bit late. It was, you can see here, it was supposed to go online in 2018. But it's a very large structure that holds about 27 million gallons of overflow. And that also is released to the treatment plant. There's a high rate treatment system. It's basically a treatment process that's going to be on the end of that tunnel to treat any overflows that occur from the tunnel. And then we're in design right now on another tunnel called our Northside Interceptor Tunnel. And that's supposed to be online by 2026. And then also I'd mentioned there's treatment plant improvements where we've basically expanded the treatment plant. And we've got about $120 million worth of work going on as we speak at the treatment plant. This is a view to show the solution that we're employing at various locations around town. The light blue are storage locations. The yellow are storage tanks. The red depict separation solutions. And the green areas are green solutions that we've come up with. And I'll talk a little bit about each one of these. These are the 2 tunnels and the areas that they collect. What these maps show you are, this is how we delineate basically a sub-watershed for the area, and 18 in this particular case where I'm highlighting represents the regulator structure that regulates flow from this area. So all of these rack locations depicted by the numbers are controlled then by this tunnel structure that I mentioned. It's the Ohio Canal Interceptor Tunnel. Like I said, it was completed in 2019 to the tune of about $290 million. I'll show you some more slides about that in a little bit. And then the Northside Interceptor Tunnel is another tunnel that'll be along the north side. If you're familiar with where the Gorge Dam is, it'll basically run along the southern edge of the Gorge Reservoir and convey flows to the main interceptor that's located down in the valley. These are some photographs of the OCI tunnel. This one was taken about 2 years ago. If you're looking close here, and I might be able to zoom in because I'm not in presentation mode, you can see the tunnel outlet, which is right up here. That's actually about a 30-foot diameter hole. So just to give you some perspective, this was because of the topography here, we were able to gravity flow sewage and waste and stormwater into the tunnel. And then we were also able to gravity flow out, which is sort of unusual. There's a number of communities that are using tunnels as a solution, but they're either pumping in or pumping out. And we have the luxury, and it's truly a luxury, of being able to gravity flow in and gravity flow out. And so the tunnel boring machine made this what's called a portal entry into the side of the hill here down off Hickory Street. You see Hickory Street in the background here. And they were able to then bore underneath a little over a mile into downtown. And this tunnel actually terminates near Exchange and Main Street. If you're familiar with where the 69 Taps bar is, it's the tunnel ended right behind that facility. This is the actual tunnel boring machine itself. It was actually built up in Solon, Ohio, so pretty close. So just to give you some perspective, you can see the gentleman walking below there. The actual bore diameter was about 30 feet, and the finished inside diameter of the tunnel is 27 feet. So this is one of the drop shafts that's located at the end of the tunnel. This is the location right behind 69 Taps bar. And if you look closely, you can see that's actually an excavator machine. This is down at about 120 feet depth. And we had to go another 70 feet below this. Let me zoom in, you can see guys standing down there. So this shaft was 45 feet in diameter, and it was necessary to build at this diameter because we had to have a location where we could take that massive boring machine out of the tunnel once the bore was completed. Once you get down to this, we were actually mining in shale, so they were using a pneumatic hammer to kind of break up the shale, and then switching out a bucket, putting a bucket on there and actually digging it out. And as they went down, they shot rods into the walls to support the walls to make sure that they didn't get any cave-in or material sloughing off to where it would hit somebody in the head, and they were working down below. Zoom back out here. This is another view looking down at that location. Actually riding down in a bucket, basket, I should say, being lifted by the crane down into the hole. This is where the actual boring machine came through that shaft. And you can see a guy standing down there. So this is about 190 feet deep at the tunnel outlet. That's actually me standing there in front of the boring machine after it came through the shaft. This is the finished tunnel. Well, actually, before the utilities were taken out. The large duct you see going across the top took fresh air up to the front where the boring machine was located. And then this is on the left side here, you see this is actually a conveyor that would convey the boring material. As the boring machine would bore, it would obviously remove material, so that was being conveyed out of the tunnel. And then there's a couple conduits here that are taking power up to the machine because it needed power to operate, obviously. Little better perspective here on how big this thing is. This is a guy walking here. These are a little bigger. Subway tunnels are typically not this big. They're about 20 feet in diameter. This ends up being 27 feet in diameter. And you're looking at the backside of the tunnel boring machine itself there. So definitely an interesting project, especially for me as a mechanical engineer. I know there's some mechanical engineers on the call. Not something you think you would typically get involved with, but a lot of mechanical application, obviously, on this boring machine. You know, in most of the disciplines, obviously you need a civil engineer to work on the geology and just, you know, the structure itself. But then also you need, you know, electrical engineers to design the power systems necessary to run this. So basically all disciplines are necessary. This is a near finished view of the end of the tunnel. So this tunnel, what we call the tunnel diversion structure, was built here. This is how we regulate flows coming out of the tunnel, so that we can limit the amount of flow that goes to the treatment plant. There's a control building here that's got backup generation and all of the SCADA controls to actually operate this facility remotely from the treatment plant down in the valley. So getting into some of the other solutions, these areas in red were separated. So we actually went in and physically separated the storm sewers from the sanitary sewers in these areas to eliminate overflows. So that was the solution in those particular areas. These locations shown in green are areas where we used a green solution. So basically what we did, we actually went in, for example, down here in this Rack 3 area, which is down in southeast Akron, kind of near Goodyear. We actually went in and put pervious pavement in. We put in underground stormwater storage for infiltration, and just some of those other ways where we're actually offloading the stormwater out of the system, so it wouldn't inundate the combined sewer. And typically engineered soils were put in place so that those waters could seep into the ground and not into the sewer system. These areas shown in yellow are areas where we have storage basins. Some of these are quite large. The Rack 12 storage basin, which takes a lot of flow from the impervious area around Chapel Hill, that's a 6.5 million gallon basin. And all of these basins are operated remotely from the treatment plant. So we've extended fiber optic cables out to each of these locations. And so all of the control, and we do quite a bit of video at these locations, but that's all done remotely at the treatment plant. Just to give you a little more flavor of what some of these basins look like. This is a basin that we built behind Elizabeth Park Apartments, kind of below the Y Bridge, if you know where that's at. It was our only round basin that we put in, and it's 124 foot in diameter. It was about $11 million at this location. What these numbers mean is this location used to discharge to the stream 35 times a year to the tune of about 12 million gallons. And so since we've built this structure, those 35 events have gone to zero in the typical year rain event. This is what that basin kind of looks like more from a side view. You can see we've got washdown systems. These are actually all automatic washdown systems. So the operator at the treatment plant can activate these washdown systems, and these move about automatically to make sure that they get full coverage and wash down any material. A lot of this material you see because of this event was leaves that were pushed into the system off roadways. But these hose down systems wash that material down, and that material goes to the treatment plant. This is another location, Forge Field, also down in the valley. This is about a 2 million gallon capacity. This is a different view of that location. So basically it's just a big concrete holding tank. On this side you can see these stainless steel, these are called tipping buckets, and that's how we wash down the tank once it's dewatered. These fill up with water, and they're basically, the center of gravity is off center, and it's real similar to if you ever went to Geauga Lake back in the day and they had that big vessel that would hold water and eventually it would tip over. Same concept here. Once the center of gravity shifted, these things tip automatically, which is nice because there's no mechanical, part to actually cause the tipping action. It's just done by gravity. And they tip and dump a ton of water to wash down the bottom of the tank. This is actually just a view of an overhead pipe that's conveying those flows to the Rack 14 basin. This view shows, this is a typical amount of flow, typical amount of flow coming into that sewer. The flows are regulated by that hole there. That's a 10-inch diameter hole. So any normal flows that can flow down that 10-inch hole go to the treatment plants. And during a rain event, when that large 48-inch diameter pipe on the right side starts filling up, it inundates that hole. The water can't all fit down it, and then it jumps over that wall and is directed to the storage tank. So just to give you an idea of what one of these regulators look like. We've done some work to our main outfall sewer. If you've ever driven down Riverview Road between Smith Road and Bath Road, on the right-hand side as you're going north, you see a large, it's basically a pipe, although it doesn't look like a pipe. It looks like this on a cross section. We call it a basket handle sewer. But we, as part of our consent decree with the federal government, we had to reinforce this original sewer that was built in 1928. It's a 3 rings of brick. So we actually reinforced it with a shotcrete and a reinforcing steel to ensure that it's ready for the next 100 years. I wanted to give you an idea of how we control this. So if you can imagine, this is our sewer system shown linearly, so basically in a straight line. And we've got all of these storage basins along the line of the sewer on its way, including the tunnel here, all the way to the WRF, which is the water reclamation facility. But you know, the operators at the wastewater plant need to know, okay, when do I dewater this tank or that tank, or when do I fill a certain tank? And so we've worked with, I don't know if you guys have ever had classes with Dr. Miller, Dr. Chris Miller. We've worked with Dr. Miller and also a company called MNet out of South Bend, Indiana, and they put together algorithms to hydraulically model the system, and in our particular case, this system, to show storage volumes and control features that allow us to control the flow from these basins. And all of that goes into these algorithms, and also the capacity of the treatment plant. And that is used, we call it a decision support system, to where we allow the operator then to decide whether automatically or manually how he's going to operate and dewater the system to get it ready for the next storm event. So a lot of work went into that. It's called real-time control, and it's kind of cutting edge stuff. We're actually including a component to where in the future we'll be able to look at upcoming precipitation, and based upon the precipitation and how it falls in town, we may be able to ready certain storage tanks sooner than others, so that we can try to capture as much CSO as possible. So that's a little bit about the collection system. I'm going to breeze through a little bit here about the treatment plant, just get a little bit of the history of Akron's sewage treatment plant, and then talk a little bit about some of the sustainability things that we've been doing. The current plant located down in the Merrimack Valley, where some of you may know where that's at, is not the first treatment plant. The first treatment plant for Akron was built over on Cuyahoga Street back in 1916. And the unique thing about this location was that basically the treatment plant was undersized before it was completed. So it was sized for 8 million gallons per day of flow. And when it was completed in 1916, it was already seeing 15 million gallons per day of flow. So they were trying to push 8 million gallons through the new treatment plant, and then they were dumping 7 million gallons of flow to the river because they just didn't have the capacity to treat it. And the reason for that was because of the rubber industry and just the city growing exponentially. And right away they knew that this location was not big enough to build a treatment plant sized to treat all of that flow. And that's when they went to our current location and purchased about a little over 800 acres to build the plant where it's located today. So the plant was put online in 1928. There was about 500 workers on site building the plant. They were kind of in a hurry because of the amount of water that they were pushing into the Little Cuyahoga River at that point, based on where the old plant was located. But nonetheless, it went into the Cuyahoga River, and then everybody downstream was upset. Boston Heights, village of Peninsula, they were all upset about the conditions in the river because what Akron was dumping in. So they hurriedly put this online in 1928. Interesting view here. I overlaid this on the existing treatment plant site, but you can see where I superimposed where the river actually laid originally. And back in the early 20s, they took these bends out of the river. Currently, the river flows along the western edge of the treatment plant in a little more straight line. But yeah, they took a couple of these big bends out of the river to build the plant. Not something that would be very easily done today, if it even at all possible. Trying to relocate a river, especially a river like the Cuyahoga River, it has a lot of historical significance. It'd be very tough to do that. So that's interesting. Just some old shots here showing, this plant was built back. They used horse-drawn excavators to peel off the topsoil, steam shovels to do large excavation. These guys here, it's eerily similar to what how concrete is laid today in terms of just the reinforcing steel. Now these guys, nobody's wearing a hard hat or anything, so safety wasn't of utmost importance. But kind of a neat old picture. Where am I at here? Another one. Let me move down. I'd mentioned there was about 500 workers on site. They actually had cafeteria. They built these mess halls basically, and they fed the workers that were working here because back then the Merriman Valley isn't like what it was today. It was out in the sticks, and for these guys to potentially leave the site to go get something to eat or whatever just wasn't really possible. A lot of them didn't have cars. They rode buses or something to the site. So they actually fed them on site. Kind of a neat old picture of a submersible pump here that they were testing. Hopefully that's some temporary wiring. Wasn't anything permanent. This is a little later on, back in the 50s. Kind of cool. These old single axle dump truck or cement trucks. A little smaller than what you see today. And finally, kind of a cool old picture. This is what's called a Horton sphere. So they did have an anaerobic digestion process where they generated biogas, and they stored the biogas in this round cylinder. As you guys know, stresses and strains and stuff, you can put a lot of pressure on a vessel of that configuration. That looks like something on the planet Mars or something. So getting into the treatment plant, the process itself, process is pretty linear. Flow comes in, we do some screening and grit removal, we meter it, we'll divert it to some on-site retention if we have to. We do some primary settling where we slow the flow down to try to get the organic materials to drop out. The bread and butter of the operation is called our secondary process. It's basically where we mimic what goes on in nature in terms of using biology to consume the organics that's in the water. We separate those organics and the good bacteria, the bugs we call them, in these clarifiers, and then we ship the water then to disinfection, where we add basically bleach to it before it's released to the Cuyahoga River. And then this whole scheme on this side depicts what we do with the biosolids that we pull out of the process. I mentioned the operations is done remotely. It's done at this location. This is located in our administration building at the treatment plant. Highly computerized, highly automated. We do use a lot of closed circuit TVs to monitor things. You can see here up on some of these screens, there's a very good trending package which is kind of good, especially for the process guys if they want to do some cause and effect situations. You know, we may have a pH drop at a certain location of the plant, and they can make some trends to try to figure out why that pH dropped. Was it because of a return flow, or did something come into the plant? Is there a temperature situation? So a very powerful tool that we can use to operate the treatment plant. Ultimately, the flow goes into back into the Cuyahoga River. Barely see the Bathrobe Bridge there in the background, just to give you some idea where this is actually located. But even as you can see here on this day, the water coming out of the treatment plant is a lot cleaner than the water that's actually in the river, at least from a turbidity standpoint. During the summer months, the river flows. This is probably an average day of flow in the river, but during the summer months, the river flows are very low, and we get to the point where the treatment plant is making up at least half of the flow in the river at that time. So moving on to the sludge side of things. So, you know, the goal of the treatment plant is to try to separate the solids that are in the water from the clean water. The clean water we put back into the river, you just saw from the previous slide. In this location here, you can see two different types of sludges that are going into a tank where we actually mix these sludges together. Before we send them for processing, we generate about 175,000 gallons per day of sludge. So this is where I'm going to talk a little bit more about the sustainability things of what we do. And I wish my slide could show here, but a good quote I found one time: "It is the responsibility of government to set an example for a sustainable community in energy consumption and energy conservation, and in minimizing adverse impacts on the environment." And that's what we were doing with this project. We actually previously would take that sludge that you saw in that previous slide, and initially we would burn it. We had an incineration system at the treatment plant where we would actually take that sludge and burn it into an ash, and then that ash was disposed of in the landfill. And then progressively, the city went to a little more of a sustainable solution. We are actually composting the sludge, where we actually took that material and mixed it with sawdust and bark and made a compost material that we actually sold in bags in bulk. But that too is a process. It was very difficult to do in this part of the country because of the cold winters, and it was very fraught with odor problems, as you may or may not know. So we actually came up with a different solution called anaerobic digestion, which is something that's not new. The actual way that we're actually using the process is new, but we generate a biogas from that process through anaerobic digestion. So basically, it's anaerobic, which means it's in the absence of air. And we take that sludge material and we blend it together and hold it for a while to where it actually starts digesting, and it generates gas, digester gas, methane gas. The methane gas itself has about half the heating capacity of regular natural gas that you or your parents might heat your homes with, but nonetheless it has value, and it is explosive. So we generate this biogas that we capture, and then we make electricity out of it. So this video or this picture shows the original composting operation, the footprint of the plant. Very large facility. If you've seen it driving down Riverview Roads over here, you see the facility. We utilized a portion of the facility for dewatering, and you can see in phase one. So we actually phased our conversion to anaerobic digestion. We built, because we weren't really sure about the process, so we built phase one, which did about 1/3 of our sludge volume that we generate, and that's depicted by this yellow footprint. That we had a digester, and then it was actually a primary and a secondary digester with an engine cogeneration system. And then once we got familiar with and comfortable with the process, we decided to go full 100% and convert all of our composting operation to AD. and that's shown by the facilities that were built in the red. So you can see, just looking at these red figures, this is basically what we're using now to process the sludge compared to this entire building that was necessary for the composting operation. We are also talking about converting then this, because now this phase 1 system is unused, but we are thinking of converting this to a merchant facility. Basically, we would bring in organic wastes from restaurants, or we may start a small organic waste recycling program in the city of Akron. So people, similar to how they separate their plastics and paper and those types of things and recycle those, they would have a container to recycle their organics. So if they're making a salad or something and they've got pieces of carrots or whatever that are unused, or pieces of lettuce, or pieces of unused meat, fat or something like that, they can separate that out and potentially be brought here to an organics receiving facility, where we would take that, digest it, and convert it into biogas to generate additional electricity. So the generation portion of our 80s system, this is basically what it looks like from an overhead view. We've got 2 primary digesters here. These are the round digesters. They've got flexible domes on the top to allow for the variations in pressure as the gas builds. Then we draw that gas off. We have to scrub it before we put it into these engines that are kind of shown here. These 3, they're all identical generators that house 600 kW engines. Here you can see a little closer what they look like. But that gas then is converted to electricity in these generators. And we even went a step further in terms of sustainability. As you know, an internal combustion engine generates heat as it's operating. So we have these packages on the side. These are actually heat exchangers that capture the engine heat because of the combustion, and we're actually heating oil that we use in the process to dry the sludge. So rather than using natural gas to heat the oil to dry the sludge, we're actually using waste engine heat from the engines and capturing that heat. So we're trying to squeeze as much as we can out of these turnips and utilize as much as possible. The electricity that we produce from these engines is enough to power about 900 homes, so fairly substantial. Now, all of the electricity that we utilize, or that we generate here, we utilize on site. So no electricity is being exported. Wastewater treatment is a process that is very energy intensive, and we utilize all of that energy on site. But if you think about it, it's energy that we otherwise would be purchasing from Ohio Edison or First Energy, our energy provider. Another project that I wanted to talk about was, we've ceased doing this, but we did this for a number of years, and I'll tell you why we had to cease in a little bit. But Hardy Road landfill is located across the street from the treatment plant. Akron Peninsula Road kind of bisects the 2 properties, but this was part of that original 800 acres that was acquired for the treatment plant back in 1928. But in 1969, it was began to be used as a landfill, just a sanitary landfill. So the landfill is now closed. It closed in 2001, but as part of the closure process, they have to keep vegetation controlled on that site. So there's basically prairie grass that grows on this large site because you don't see any trees there, and that's to maintain the integrity of the cover. But before I get into that, so when you put trash into a landfill, there's a lot of organic material in that trash, and that organic material is going to digest. It's very similar to if you've ever mowed your grass and you put a pile of grass in your backyard and you went back to it, sometimes you feel that grass gets hot. Or if you see a pile of mulch, sometimes you might see steam coming off of it. It's just the naturally occurring bacteria that's digesting that the organics in that material. So the trash that was put into the Hardy Road landfill from 1969 to about 2001 generates biogas, and for the longest time they were flaring that gas. So back in the early 90s, we actually started capturing this gas, and we were using it for building heat, because similar to digester gas from wastewater treatment, it generates about half the value of natural gas. This graph, what I wanted to show you here was if this line that shows by these diamonds, this is the trash going into the landfill in tonnage over years. And here you can see about 2001-ish is when the landfill shut down, so there's no additional trash going in. And then these two lines estimate the gas that is going to be produced from that trash. And you can see that after we stopped actively putting trash into the landfill, the gas production starts to drop off. And unless we continue to put trash into the facility, the gas eventually is going to die off as those organics are stabilized. And it dwindles down to nearly zero out in 2018 or so. And that's pretty much what we saw. So when the landfill was closed, a cover was put over the landfill. This is real heavy polyethylene tarps, basically. And this keeps water from infiltrating through the trash. They're trying to minimize the amount of leachate. Leachate is the water that kind of results from the trash, whether it's through snow melt or precipitation, or the trash itself just breaking down and creating or making water. This barrier blocks precipitation from coming in and to minimize that leachate. But what it does then, it basically puts a lid on top to allow us to pull off the gas that's being generated by the decomposition of the trash. So these wells were actually put down through the membrane. These wells are just basically perforated PVC pipe that extends down into the trash, and it's just operated on a vacuum. There's a blower on the other end of this suction line that goes to the flare. So the gas just gets pulled out from underneath the tarp from the trash here out through the suction line and over to the flare or the gas cleaning system. And that's how we get the gas off of the landfill. It was directed then to this lower picture is our gas cleaning skid. As you can imagine, there's a lot of moisture in that gas that has to be taken out. And there's also some H2S, hydrogen sulfide, that needs to be taken out before we put it into this engine generator. This is a very large 1100 kW engine generator that used the landfill gas to burn to generate electricity. And we would generate about 40% of the electricity requirements for the treatment plant. And in conjunction with the electricity that was generated through our renewable energy facility, we were able to almost get the plant to neutral. And that's what I'm trying to show here in this slide. And you have to look at the scale on the bottom. So I actually started out because I wanted to show back in 1994, we were drawing nearly 50,000 megawatt hours of power for the facility. Now you can see there's about a 12 to 13 year difference between these two lines. But during this period of time, we spent a lot of money, a lot of effort to reduce the amount of electricity that we required to process the wastewater down to this level in about, this was probably about 2006. So a lot of effort, a lot of good that came out of that. Back in 1994, we were spending probably $240,000 a year or a month, on electricity. So imagine that, you know, your parents probably spend about $100 a month on electricity. We were spending $240,000 a month. So the payback on a lot of the things we did was very short, if you can imagine, because now, well, if you go over to 2020, we're spending about $60,000 a month on electricity. So big savings there. But what I wanted to show in this graph, if you kind of squint, maybe looking at it and just kind of focus on the black, you can see the reduction in the continued reduction in the amount of energy that we have to purchase from First Energy. Now, there's a little bit of an uptick here in the last couple of years. That's largely due to plant expansion and the need for a little bit more electricity to be able to treat more water. But the different colors here, I had mentioned before that we phased the ADS process. So the red depicts the electricity that was generated in the first phase of the ADS. So it's a little small, but it was just a pilot project. And then we fired up our landfill gas project, and we started making electricity that significantly here in probably 2013-ish, we dropped First Energy electricity coming into the plant, further dropped it 2014. And that's about when we put the second phase of the digestion system online. And you can see a fairly consistent production of electricity over the last 5-6 years from the ADS2 process. And here you can see in 2018 when we actually shut the landfill gas system down. And as you might recall from that chart, that's about when we predicted that the production of gas from the decomposition of the trash was going to basically phase out. And that's when we got to the point where we really couldn't continue to run that big engine with a little bit of gas that was being produced. We had to shut the system off. So now we're just relying on our ADS2 facility to offset the amount of electricity that we have to buy from First Energy. So very sustainable. Basically, we're reusing a renewable source in the form of sludge that we separate from the wastewater to generate electricity to offset the electricity that would otherwise perhaps would be being generated from coal, or you know, there may be some nuclear in there or solar or wind, but we're actually generating from a renewable source from the wastewater. So to finish up here, the facility itself is performs very well. We regularly meet all of our permit requirements for discharging flows to the river. We have a very dedicated staff of people that you know, there's some engineers in the group. We've got skilled chemists and biologists, technical people to maintain the computer systems. But it's a 24/7, 365, very dynamic operation because of the impacts of weather and precipitation. And we like to say that we are number one in the number two business. So that's basically all I have. But I'd be happy to answer any questions anybody has.
I guess my big question would be, what prompts the city to try and be more sustainable? Like, is it more to comply with the regulations, or is it just because it's a good look?
Yeah, a little bit of both. I mean, you know, as I said up here somewhere, you know, it's basically our duty as stewards of the environment to try to set an example for stewardship and sustainability. And you know, it's somewhat driven by financial aspects. I mean, as you can imagine, when we were spending $240,000 a month for electricity, and we can drop that to $60,000 a month, there's some motivation there. But yeah, so for those reasons, setting a good example, as well as just the need to try to do more with less and try to be fiscally prudent, I guess. Good question, though.
I have a question. So, because you are kind of repurposing the sludge before getting rid of it, does that change how you dispose of it? Or, like, I guess, what do you do with it once it's anaerobically digested and you've got all the energy you can out of it? Where does it go?
Yeah, that's a good question. So it doesn't just vanish. So while it does produce gas, there is a residual, and it's actually digestive material. So we actually market that material, and it's basically sold on the wholesale market to topsoil blenders, or a large market is for potting soil. Now, up along Lake Erie, I don't know if you've ever driven up along the lake, there's a lot of nurseries up there. And a lot of the material goes into a potting soil mix that they use then when they grow shrubbery or flowers or plants or those types of things. So the material goes into that. I also mentioned topsoil blending. There's some operations where they actually will have a very clay type soil, and then they'll blend in this material that we make to make more of an amended product that just has better value as a topsoil than just the clay. So yes, there is a residual. We do, because of the efforts that we take with the industry in the city of Akron, we do have what's called Class A unrestricted material. So if you want to use this material to grow tomatoes or potatoes or something like that in your home garden, it's unrestricted for that type of use. The metals content in the material is low enough that allows that.
Okay,
that's a good question.
That's interesting to me, because I know that I don't know, I feel like there would be kind of a stigma about using it, but you know, if it's safe and you know it has nutrient content that soil needs, why not? So.
Yeah, it's funny, when we used to make compost, we used to make about 80,000 yards a year of compost. And we had, little old ladies would come down and buy a couple bags for it because they love the stuff to put on the rose gardens or whatever. And when we stopped making compost, we heard a lot of complaints from those folks that just become so used to it, and they really loved it. But we're trying to get them turned on to this new digestive material. It's a little different texture, a little different qualities, but it definitely has the same benefit as the compost.
Does anyone else have any other questions? And if you don't have a microphone or something, you can type it in the chat and I can ask it for you. All right, Mr. Gresser, do you mind if we send out your email so that if people have questions?
No, sure, that's fine, sure. Yep.
Okay, awesome. Thank you so much for presenting. That was really interesting. Maybe it's just because I'm a civil engineer, but I think everyone enjoyed it. So thank you so much. And
I was going to say, we do offer tours of the treatment plant. I mean, if at some point the ESW group would want to tour the facility, we'd be more than happy to show you guys around. So you could just, let us know if that comes to fruition. It's kind of cold right now to be touring the treatment plant, so maybe something later in the spring or something if you're interested.
Okay, yeah, I will bring that up to our members. I think that would be a really interesting and educational experience. So
okay, great.
All right. Well, thank you everyone for coming. If you didn't get a chance to watch the whole thing, or if you had a friend that didn't get to see it, this will be posted on YouTube. So yeah, thanks for coming.
Thank you.
Thank you. Have a great night, guys.